Okay, so let's start with a not really a summary, but a bulleted list of things you learned this week. What are sort of the main topics? Law of sine and cosines. Identities, that's a big one, and this is a common point of difficulty at this point in the class, so we will definitely spend some time going over how to prove identities. What else? Polar coordinates. Sorry, what? Oh, like double angle identities and yeah, okay, sure. Yeah, so we have double angles, the sum and difference identities. Yeah, good. Factors? Oh, vectors, yes. Yeah, the very last lesson this week was on vectors. And there's something else with polar coordinates. Complex numbers and how to graph them and represent them with polar. Cartesian and polar form of complex numbers. Okay, so that's a good list. Let's move on to the questions here. Should we have the law of cosines memorized for the quiz? No, you should have it written on your note card. And can we go over a question using the identities? Double angle, symmetry, etc. Okay, so there's different ways that you can use the identities. You can use them to prove an identity that hasn't yet been proven, or you can use them to find the value of an angle. Like let's say if I wanted to know the sine of 15 degrees exactly. So I could put it in my calculator and get an approximation, right? But if I wanted an exact value, I could say, well, 15 is the difference between 45 and 30. And I have a formula for the sum or difference of a sine. Right? I do have that now. Yeah. Okay. So we had a formula that the sine of A minus B, I believe it's the sum difference for sine is sine, cosine, cosine, sine. I can't remember. Yeah, so this trig identities reference sheet you can use on the next quest, and you can bring it to the final exam. You bring the whole package to the final exam. All right, so here we go. Sum and angle difference formula. So if I want the sine of A minus B, it's sine, cosine, sine, cosine, cosine, sine. That's it. Okay, so sine, cosine, cosine, sine, and then it's A, B, A, B. Yeah, so it's a subtraction. Yep. Sine, cosine, cosine, sine. Yep, and it's a minus. Okay, so if I want to do sine 45 minus sine 30, sine of 45 minus 30, which would give me the sine of 15, I can just plug into this formula. So A is 45 and B is 30, so this is going to be sine 45 cosine 30 minus cosine 45 sine 30. And I know exact values of all of those from the unit circle. Right? Okay. So the sine of 45 was 1 over root 2, or root 2 over 2, same thing. What's the cosine of 30? Root 3 over 2. The x coordinate at 30 degrees on the unit circle. Cosine of 45 is 1 over root 2. The sine of 30 degrees, 1/2. So let's just remind ourselves, if you have forgotten, how to find those values on the unit circle. So I'm going to pull up a picture of the unit circle. This is also in your reference sheet, and you can use it on tests and quizzes. So when I want to find the cosine of 30 degrees, you find the 30-degree angle right here. And then the x coordinate is the cosine of that angle, and the y coordinate is the sine of that angle. So that's how you find the exact values. Okay, so you can find exact values without a calculator. And then we just simplify this. So this is going to be root 3 over 2 root 2 minus 1 over 2 root 2. Those have the same denominator, so I can just do the subtraction where I subtract the numerators. So this is root 3 minus 1 over 2 root 2. And you could rationalize the denominator. I'm not going to require it, but many teachers do require it. So just to briefly show you, multiply both the top and bottom by the square root that's on the bottom. Rationalizing the denominator means get rid of the radicals in the denominator. Okay, so root 3 times root 2 is root 6. 1 times root 2 is root 2. And root 2 times root 2 is root 4, which is 2. So 2 times 2 is 4. So that or this, perfectly acceptable answers. This is with a rationalized denominator. Not required to do that in this class. But many people, by the time they get here, are conditioned to do that. So it's completely fine if you do. Or just so that you can recognize that those are the same, because often, like answers in the back of a book will be rationalized. So just so that you can recognize it as the same value. Yes, if instead of using 1 over root 2, I used root 2 over 2, you would have come out with this value. Yeah, good. So that's one way you can use one of the identities, right? The sum or difference identity. Other ways you can use identities involve proving new trig identities, and I have some questions on those, so let's go through one. So we want to prove that 1 minus cosine theta divided by cosine theta is the same thing for any value of theta as tangent squared theta over secant theta plus 1. This is from your notes. So first thing you should do is, before you start working really hard to try to prove it, prove to yourself in a simpler way than algebraic manipulation that these are in fact the same. You don't want to do a ton of work trying to prove it if they're not actually equal. Okay, so I'm going to use Geogebra. I'm going to graph each side of this and make sure that they have the same graph. Okay, so I'm going to graph y equals 1 minus cosine theta over cosine theta. We'll call that f of x. Parentheses around my numerator. 1 minus cosine x, because you can't put thetas in GeoGebra, you can only use x's and y's. All right, so we've got 1 minus cosine theta divided by cosine theta. Okay, so there's my graph of f of x. Seems like a perfectly okay window to use. All right, now I'm going to graph g of x, which was tangent squared theta over secant theta plus 1. Okay, so tangent squared theta is shorthand. I'll write it on the. Okay, so tangent squared theta is shorthand for the tangent of theta squared, right? The reason we use the squared theta, putting the squared in that weird place, is because it's very confusing unless you write parentheses. If you just write tangent theta squared, do you mean take the tangent of theta and then square it, or square theta and then take the tangent? Right? So just to avoid having to write 2 extra symbols of parentheses, we have decided to put the squared, when we mean take the tangent of theta and then square it, you put the squared before the theta. So it's clear we're not squaring the theta, we're squaring the tangent. So GeoGebra does not know this notation, so you have to write the tangent of theta in parentheses and then square it. Same with your calculator. Okay, so the tangent, that's the numerator, tangent squared theta. Okay, so I have to put parentheses of tangent x and then square it. And I've got parentheses still around the whole numerator. And then I'm going to divide by the denominator, which is secant theta plus 1. I'm not sure if GeoGebra knows secant. I think it does. Plus 1. Okay. And when I graph it, it's the exact same graph. So, and if you're not sure if it actually graphed, you can just change the colors. Like, I want to go to object properties, color, and I'll do like red. And then you can see there's like red and black there. F of x and g of x. You can make g of x blue. And now the lines are purple because they're red and blue. So it looks like graphically, these two look like the same thing. Like no matter what theta you put in, you get the same y value. So that means that it's going to be worth our time to prove this algebraically, because I know that it actually seems to be true graphically. All right. So my first tip for trig identities, draw a line down the middle, because this is different from solving an equation. You don't do the same thing to both sides, because you're not trying to solve anything. Because there's an infinite number of thetas that make this equation true. Every single theta makes this equation true. So you're not trying to solve for a single theta. You're trying to prove that this is always true. So I draw this big line here to kind of remind me I have to stay on one side or the other. And then what I do is I choose the more complicated looking side and try to make it simpler. So when you look at that, which side seems more complicated to you? The right side. Yeah, it's got a squared in it. It's got a tangent and a secant, which are more complicated than cosines and sines. So I'm going to work on the right side first. And because my left side has just cosines in it, I'm going to try to turn all of this into cosines and sines. Anytime you have something other than cosines and sines, it's a good idea to turn it all into just cosines and sines, because everything can relate back to how it relates to cosine and sine. And if the left side also had tangents or cotangents or cosecants, non-cosines and sines, I would do that one also. I'm going to start on the right, make everything written in terms of sine and cosine. So how can I rewrite tangent as sine and cosine? Sine over cosine. Yeah, so instead of tangent squared, I'm going to do sine squared over cosine squared. All right, so I've just replaced tangent with what it's equal to in terms of sine and cosine. Then I've got my big division sign. How can I rewrite secant in terms of sine and or cosine? 1 over cosine. Yep. Okay, so it's a good idea while you're working on proving trig identities to have this sheet out in front of you, right? This has everything, right? Here's the tangent identity. It's sine over cosine. And then I have reciprocal identities somewhere, I think. Oh, they're not written on here. You might want to add them so that you know what the reciprocals are. The reciprocal of sine is cosecant, etc. Oh, they're on another paper. Okay. They're on the 6 trig functions, maybe. There we go. Yeah, relationship between the functions. And the Pythagorean identities are there too. Again, you'll have that on the quiz. Okay. So now I've got this ugly mess here. Sine squared over cosine squared, all divided by 1 over cosine plus 1. So this is a compound fraction, fractions within fractions. So I want to make this a single fraction on top, done, right? Divided by a single fraction on the bottom. So I want to work on this denominator and turn this into a single fraction. So I'm going to add those, 1 over cosine theta plus 1. How do I add those two things together? What do I need? Eileen. Common denominator. What's my common denominator going to be? Cosine theta. So I could rewrite that 1 as cosine theta over cosine theta, right? Now I have the same denominator, cosine theta, so I can add the two fractions. Okay, so when you add fractions, you add the numerators. So first I'm going to copy down my sine squared theta over cosine squared theta all over. And now adding fractions, you add the numerators. 1 plus cosine theta, that's just 1 plus cosine theta. We can't simplify that. Divided by the common denominator, cosine theta. So now I've written this as a fraction divided by a fraction. One fraction divided by another fraction. How do you divide fractions? Multiply by the reciprocal, right? Flip and multiply. Okay, so instead of writing sine squared theta over cosine squared theta, instead of dividing that by this fraction, I'm going to multiply by the reciprocal, cosine theta over 1 plus cosine theta. Now I can cancel a little bit. I've got a cosine theta here and a cosine theta quantity squared in the bottom, so that's going to cancel one of them. All right, so if I simplify this, I've got a sine squared on top divided by cosine theta times 1 plus cosine theta. All right, when you multiply fractions, you multiply across. So I actually multiply the denominators together. Okay, so I've done a bunch of simplifying. I rewrote everything in terms of sine and cosine and sort of simplified out as much as I can. Now I have to take stock of where I am. My goal is to make the right-hand side. I've done a whole bunch of manipulation and simplification on the right. My goal is to make it look like this. I want it to come out to look like 1 minus cosine theta over cosine theta. So look at where I am and where I want to go. and I say, okay, I need a cosine theta all by itself in the denominator. I currently have a cosine theta in the denominator, but there's some extra stuff there that I don't want to have there. So it would be great if I could like maybe cancel a 1 plus cosine theta. If I could get a 1 plus cosine theta into the numerator, I'd cancel them and I'd have my plain old cosine theta in the denominator. All right. And I want my numerator only has cosines in it, right? Is there some way that I can, some identity I can use to rewrite sine squared theta in terms of cosine? Pythagorean identity, right? So this is just a little aside over here. Remember that sine squared theta plus cosine squared theta equals 1. So if I wanted to put something in place of sine squared theta, what would it be? 1 minus cosine squared, right? Solve this thing for sine squared theta, and you get 1 minus cosine squared theta. So I'm going to come over here, replace my sine squared with 1 minus cosine squared theta. Okay, so now I've accomplished that my numerator only has cosines in it, but I have a squared that I want to get rid of, and I've got the extra factor in my denominator, 1 plus cosine squared. If instead of saying 1 minus cosine squared, that numerator said 1 minus x squared, how would you factor that? How do you factor the difference of two squares? Yeah, that would factor to 1 minus x, 1 plus x, the difference of two perfect squares. I can apply that because this is 1 is a perfect square, it's 1 squared. Cosine squared is a perfect square, it's cosine squared. So I can factor that the same way I would 1 minus x squared. Okay, so this is 1 minus cosine squared would be 1 minus cosine theta times 1 plus cosine theta over cosine theta times 1 plus cosine theta. So all I did was factor my numerator, and now my 1 plus cosine thetas cancel. And 1 minus cosine theta over cosine theta, that's the left-hand side of the equation. Right, so there it is. Done. Aren't they the best? So we started by looking at the graphs of the two, right? And saying, oh, they have the same graphs, they have to always be the same. So this is really strong evidence that they are always the same, but you can't look at the entire XY plane. It's an infinite space. So based on this graph, I can say they're the same for every x between -3 and 10, right? But no matter how much of this I put in the screen, you know, even if I shrink this and I say, oh, okay, now I know that it's true from -20 to 80. That's still all I can say. It's true from -20 to 80. Yeah. But it's still, you still haven't proven that it's true for every theta value. You've proven it's true for a lot of theta values, but not every. So yeah, it depends on your purposes. Yeah. If you're an engineer and you know that you want to use this identity, you know, between, say, theta's temperature or something, I'm going to use this from -10 degrees to 45 degrees. I have to make sure that my bridge is going to withstand that temperature range. You probably don't have to do a whole proof that it's true for every single theta. You could look at the graph in the range that you want and say, good enough, right? Yeah. And then it's different. That's a great question, and I will find one, but I don't know one off the top of my head. Okay. I'll find one. They do exist. I don't have one off the top of my head. Okay, so we want to show that these two are equal, because apparently Wiley plus told us they're the same. Okay, so I need sine of 3t. So let's delete these. And we'll do f of x equals the sine of 3x. So there's one graph. And then my other one is sine 2t cosine t. T of x. Sine 2x cosine x plus cosine 2x sine x. Cosine 2x sine x. Graphs look the same to me. Yeah, that looks like one of the angle sum identities. So yeah, the graphs are the same. It's purple now. Mm-hmm. Yeah. They're not the same. Okay. H and J. So we got to choose that one. Which other ones are? C, D, and F are the same? E and G. Let's try that one. Okay. Yep. Nice. Yeah, so it marks H and J as the same. Ah. Show solution. Ah. H and J. They look the same. H is over here and J is over here. H and J. That's okay. Yeah, one way to recognize that these are the same is to recognize that this is the formula for the sine of 2t plus t. If you were to apply the angle sum formula to 2t plus t, which is 3t, right, you would do sine, cosine, cosine, sine of the a and the b. So let me show you my little way of remembering the sum and difference. So if you want the sine and the cosine, it goes sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. Sine, cosine, cosine, sine. Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. It is, yeah. Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. The first of the sine has to do with the plus and the minus. So instead of plus minus, it becomes minus plus. Cosine, cosine, sine, sine, sine. And then you put in A's and B's. Same sign. I mean, you're going to have it on paper, so there's no need to know this little rhyme, but if you're interested. So if you want the sine and the cosine of the sum and difference of A and B, it's sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. But this sign is SIGN, right, for plus and minus. Yep. So that's my little way of remembering that. From its past behavior, John knows that the value of the stock has a cyclical component, which increases for the first 3 months of each year, falls for the next 6, and then rises again for the last 3. In addition, inflation adds a linear component to the stock's price. So John is seeking a model of this form. Okay, so MT plus B, that's linear. And then this sinusoidal part is going to try to capture the fact that it goes up and down. So it's not completely a sinusoidal function because it's not exactly the same year after year. It's also continuously rising linearly. So we have a sinusoidal piece of the function, and then we have a linear piece, trying to capture both phenomena. Okay, so here's the data. We have some stock prices, T months since January 1st. Okay. And what we're looking for is find values of M, B, and A so that F fits the data. Okay, so we need to figure out what values to use here. So F of 0, right, when T is 0, that's January 1st, we have M times 0 plus B plus A times the sine of 0, right? Because pi over 6 times 0 is 0. Okay. All right, so M times 0 is 0. What's the sine of 0? Is 0. So I have 0 plus B plus A times 0, which is 0. Okay, so that is 0. This whole thing is 0. So this is just B, right? Okay, so that, according to the data, is 23. So we know the value of B because we know the value of the function at 0. Okay, so that's one thing. So now I know that f of t is equal to mt plus 23 plus a sine pi over 6t. So now I can pick another data point, see if I can solve for something else. Let's use January 1st again, $53. So what value of t is that? Is this measured in days? T is measured in months. 12. 12 months later, you land at the exact same date. Okay, so f of 12 is equal to 12m, right? I'm putting in a 12 for t, plus 23 plus a times the sine of pi over 6 times 12. What's pi over 6 times 12? 2 pi. Okay, that's why I chose 12 as the next thing to plug in. Because what's the sine of 2 pi? 0. So I like that comes out to 0 because it gets rid of a variable, right? So this whole thing is 0. Because the sine of 2 pi is 0, a times 0 is 0. And then what's the answer to this? What is the value of f of 12? 53 based on the data in the table. Okay. So I now know that 12m plus 23 equals 53. So 12m equals 30. So m equals 2.5. All right, so I've got a value for m now. So f of t is 2.5t plus 23 plus a times the sine of pi over 6t. Okay, so now I only have one variable left to find a, so I can use any value of t I want, but I should use something that makes the sine easy to evaluate, right? So pi over 6 times something that would give me an easy thing to evaluate. So January 1st, that's 0. So February is 1, March is 2, April is 3, right? July is 6. That one, because that would give me pi. Pi over 6 times 6 would give me pi. Let's use that one. So I'm going to plug in a 6, and I should get 38. So f of 6 is going to be 2.5 times 6 plus 23 plus a times the sine of pi over 6 times 6. And pi over 6 times 6, that's just pi. And what's the sine of pi? No. Yes, it is. It is. Thank you. Yeah, sine of pi is 0. Oh, so that's not a good one because that makes the a drop out. Let's not use that one. Because I'm trying to solve. So if I do pi over 6 times, yeah, if I use 3, that would give me pi over 2. So let's do 3. And that's supposed to give me 38, I think it was. Okay. So 2.5 times 3. It's 4. Oh, sorry. Oh, 40, 50. Yeah, thanks. Thanks. Okay. So 2.5 times 3. So that would be 6. Was it 7.5? Plus 23. Pi over 6 times 3 is pi over 2. The sine of pi over 2 is 1. So this is plus a times 1 equals 40.5. And then I'm just going to solve for a. Yeah. So 40.5 minus 7.5 minus 3 is 10. All right, so now I have a function. F of t is 2.5t plus 23 plus 10 sine pi over 6t. Does that make sense? So it's the same procedure that we use when we try to find sort of any kind of function, quadratic, cubic, whatever. Just use points. Exponential, you use the points, plug them in for x and for y, and solve for the variables that you're looking for. Okay, so during which month does the stock appreciate the most? That is gain the most value, right? Appreciation means gaining value, if anyone has taken an accounting class. During which months does the stock gain the most value? So let's take a look at our graph. Okay, so let's call this is 2.5x plus 23 plus 10 times the sine of pi x over 6. Okay, so there's the graph of my function. You can see it has a linear component where it's just continuously going up, but it also has a cyclical component based on the time of year. And during which months does the stock price jump the most? So it might be better if I just look at a smaller, like 1 year window here. All right, so in which month does the stock jump the most? So we've got 0 to 1. We go from here to here. So that's January. And then 1 to 2, we go from here to here. So if I had to choose January or February, which is the bigger jump? January, right? This is a bigger jump than this. And then if I look at February, that's an even smaller jump. And then January, February, oh, that's March. April, even tinier jump, right? And then it's decreasing, right, up until here. So I can ignore that part. So then 8 to 9, that's a pretty tiny jump. 9 to 10, that's a pretty big vertical distance, but not as big as January. And then 10 to 11, pretty big vertical jump. I need to see more Y's. Shoot, it's gonna screw everything up if I change the scale now. Well, 11 to 12 is gonna be a big jump, right? 11 to 12 is a big jump. Is it gonna be bigger than January? I think it's gonna be the same. Well, let's see. Let's actually figure out the value. So I'm gonna graph x equals 0, x equals 1, and get the intersect. Okay, so the value at A is 23. Okay. And then I want to intersect, oops. B with f of x, 30.5. So my jump goes from 23 to 30.5. That's 7.5. That's a jump of 7.5 from point A to point B. Y values go up by 7.5. Then I want to look at the jump from 11 to 12. I could look from -1 to 0. It should be the same jump because it's got that cyclical effect. Yeah. So yeah, that's true. So let's do that. Let's graph x equals -1 and intersect C with f of x. And the value is 15.5. 15.5 to 30.5. How big is that? 15, which is bigger than 7.5, right? Oh, you're right. We're looking from C to A. You're right. It's the same. From C to A, sorry, is a 7.5 jump. Yeah. So from November to December, the month of November. No, it's the January and December. Okay. Yeah, because this is December. This is December from C to A, right? Because 0 represents January 1st. So -1 to 0 is December. And 0 to 1 is January. And the jump is the same in both of them. So it's December and January. Yep.
If you have a y of sine x, what is the slope of
Say that again. Uh-huh. Okay, so the graph of sine x. Okay, you want to know the slope of the graph at 0? So the way we measure the slope of a curve is you draw a tangent line, right? So you draw a straight line because the only thing we know how to find the slope of is a line, right? Rise over run for a straight line. So you draw a tangent line and try to find its slope, and that's actually calculus. You take a derivative, yeah. It is 1, yes, it is 1. Oh, yeah. Yeah. Yeah, the slope of that line is, in fact, 1. And to prove it to you, I would need to use a little bit of calculus. Okay. Okay, so converting into polar coordinates. So here's a little aside. there's a coordinate plane. If you have some point in the coordinate plane, you can either label it x, y, right? So you go over x, up y to get to that point. Or that's the way that we've all learned how to explain where a point is in the coordinate plane. You give its xy coordinate and you go over x and up y. Okay, now we know this other way where instead of giving x and y, you could give a radius, meaning the length of the hypotenuse, and an angle, theta. And that's two other ways, two other sort of an alternative set of directions to the same point. Give a radius r and then tell how far to rotate it up to land at the point. So this is my picture that we use to convert xy to r and theta or vice versa. So let's see, if I wanted to relate these things, I could say x squared plus y squared equals r squared, right? Because that's a right triangle. So if I want to know, if I know x and y and I want to know r, I can use the distance formula. I can use trig to figure out whatever I don't know. Like I could say the tangent of theta is y over x. So that would help me figure out what theta is if I know y and x. And if I know theta and r, I could say, well, the cosine of theta is x over r, and the sine of theta is y over r, just by some right triangle trig. And so these are all my relationships between x and y and r and theta that I can exploit to try to make conversions. Okay, so this is an equation where theta equals pi over 4. What do you think the graph of that thing looks like? A constant angle of pi over 4. It's a line, yeah, because the angle is always pi over 4, and the radius can vary, right? It's like if I ask you to graph y equals 2, that means y is always 2 and x can be anything, right? If x can be anything but y is always 2, you end up with this horizontal line. If r can be anything but theta is always pi over 4, we mark out pi over 4, and then we let r vary, so you end up with this line. If I was going to give an equation for that line in xy coordinates, what would that line be? It would be a linear equation. Yep. Y equals x, yeah. It goes through 0, 0, and pi over 4 is exactly 45 degrees, right? So this is the line y equals x without even having to bother with all my fun equations. So if you wanted to use them, I would say, okay, well, the tangent of theta is y over x, right? And I know that theta is always pi over 4. So the tangent of pi over 4 equals y over x. So what's the tangent of pi over 4? I'm pretty sure it's y equals x, but this is leading to me to think otherwise. Well, let's see what happens here. I think it's just y equals x, though. What's wrong with what I'm doing? Yeah. Oh, no. Sorry, you're right. It's 1. Yeah. Okay. Thank you. The tangent of pi over 4, right? If we draw a unit circle, the coordinates here are root 2 over 2, root 2 over 2, and the tangent is y over x, right? So the tangent of pi over 4 is 1. So if 1 equals y over x, then y equals x. Okay, so I want to prove this. I should start with a graph, right? Because a graph can give me a good idea of whether or not I believe that it's true. Okay? And believing that it's true and proving that it's true are slightly different things. Okay, so I'm going to graph the left side and the right side and see if they have the same graph. So I have secant x plus tangent x. You can just give any value of theta where they're different, and you can say they're different when theta equals, 8, and then you're done. Yeah, you just have to find one value where they're different. So look at the graph, find one value where the graphs aren't the same, because it only takes one value to be able to say they're not always the same. Yeah. All right, so let's see, this is secant x plus tangent x. And I want to get rid of all of this stuff. So I've got them both graphed here, the red and the black. You can see that the lines are both red and black. They have the same graphs. I can play with the window a little bit if I'm not totally convinced. So, oh yeah, okay. Looks like they're going to be always the same. Let's go ahead and prove that algebraically, that they are always the same. Okay, so I like to draw a big line, work on the more complicated side first. So I look at that thing and I say, well, the right is in terms of sine and cosine, nice and simple. I'm going to work on the left, put everything in terms of sine and cosine. So secant x, that's 1 over cosine, and tangent x, that's sine over cosine. So now I have two fractions, they have the same denominator. I add them by adding their numerators. The denominator stays the same, and that is the right-hand side. That's a good one, yeah. Nice and easy. You want me to start on the right side? Sure. Okay, so if I were to start on the right side, I would say, okay, the only thing I can think of to manipulate this fraction is to divide the cosine into both pieces of the numerator. So this would be 1 over cosine x plus sine x over cosine x. Sort of the only manipulation I can think of is, and then 1 over cosine is secant, sine over cosine is tangent, done. So it's really tempting to like cross multiply when you see this, right? Not allowed, right? Because you have to work on one side by itself at a time. All right, okay, so I graphed the left side and the right side. They look like they have the same graph, so I'm going to go ahead and try to prove this algebraically. All right, so this is a good one, I think, to do as an example because the left side and the right side look equally complicated to me. So I'm just going to arbitrarily pick one and try to simplify it. So I think I'll start on the left. Again, this is arbitrary. And I'm going to rewrite everything in terms of sine and cosine. That's my go-to method. It is not the only way to do it. So cosecant is the same as 1 over sine. So I have cosine squared times 1 over sine, multiply those two fractions, and I get cosine squared x divided by sine x. All right, so I take stock of where I am and where I want to go, and I say those are pretty far apart. Okay, so maybe I'm just going to move over to the right side and see what I can do with that. I'm going to rewrite cosecant as 1 over sine minus sine over 1, right? And then if I want to subtract these two fractions, I need a common denominator. What would it be? Sine x. I would take this guy and multiply by sine x over sine x. So this would be 1 over sine x minus sine squared over sine x. They have the same denominator, so that's 1 minus sine squared x over sine of x. And then I look at where I am on the left and where I am on the right, and I say, oh, well, they both have sine x in the denominator. 1 minus sine squared is the same thing as cosine squared by the Pythagorean identity. So replace 1 minus sine squared with cosine squared, and we're done. So I've made the left and the right look the same, and I worked on both sides this time. Can tell me where you started. What was the first thing you wanted to do? Make it into sines and cosines? So the only thing that doesn't have sines and cosines is the left. So I'll come over to the left and I'll say, okay, so this should be 1 over cosine minus sine over cosine squared. All right, now what do you want to do to simplify that thing? I could either do the subtraction, right, inside the parentheses, because in general, the order of operations says you should do what's in the parentheses first, or you could square it by doing, by FOIL. Which one feels easier? Yeah, doing the subtraction first, right? FOIL is going to get really pretty messy. If I was trying to do 1 minus cosine x minus sine x over cosine x times itself, it would get a little messy. I could have started right here by squaring. It would have been a little less messy, which was actually my first instinct, and then change to sines and cosines, but it doesn't matter, whichever way you like. So we've already started this way, so let's go ahead and do this way. So if I subtract, these already have the same denominator, which is sort of like begging you to just do the subtraction, right? So this becomes 1 minus sine x over the common denominator cosine x, and square it. Okay, so 1 minus sine of x squared over cosine squared, right? Because when you have a fraction and you square it, you can just square the top and square the bottom. That's the rule. Right, how do you square 1 minus sine of x? I'd have to FOIL it, so I'd have to do, I'm just going to do this a little aside on another page. 1 minus sine x squared means 1 minus sine x times 1 minus sine x. And when I FOIL it, I get 1 minus sine x minus sine x plus sine squared x, right? First outer inner last. And then minus sine x is minus 2 sine x. Everyone okay with that? This is 1 minus sine of x squared. Yes, and yeah, I'll go back to my thing. So that's all going to be all over cosine squared. All right, so this is 1 minus 2 sine x plus sine squared x all over cosine squared x. All right, so I sort of feel like I have exhausted what I can do on the left. Changed it all to sines and cosines. I squared it out. There's no obvious simplification to me. Does anybody see one? Something that you want to do to this? I could break it into 3 separate fractions. Let's take stock of where I want to go. I want this to be 1 minus sine x over 1 plus sine x. I could convert the cosine squared into 1 minus sine squared, because that will make me have all sines, which is on the right-hand side. So that might be a good idea. Okay, so I have 1 minus 2 sine x plus sine squared x over 1 minus sine squared, Pythagorean identity. So I'm almost there, except I just want it to be 1 plus sine x, and I have 1 minus sine squared. Maybe we should just move to the right-hand side and see what we can do. I want that to be 1 minus sine squared in the denominator. All right, so what if I multiply by 1 minus sine x over 1 minus sine x on the top and the bottom? It's allowed, right? Anybody have any reason why I might do that? Just to make it complicated? Well, the left-hand side is pretty complicated, what I've turned it into, right? It's like kind of ugly. Yeah, 1 minus sine squared factors to 1 minus sine x, 1 plus sine x, right? So if I multiply 1 plus sine x by 1 minus sine x, I'm going to get the denominator I have on the left. Okay, so, but I can't just do the denominator, you have to do the numerator too. Okay, so 1 plus sine x times 1 minus sine x gives me 1 minus sine squared x. If you FOIL it out, because first 1 times 1 is 1, then you have minus sine x plus sine x, and those cancel, and then you have minus sine squared x. So now I have the denominator that I have over here. So that's a good step. All right, and then if I multiply out 1 minus sine x times 1 minus sine x, I get 1 minus 2 sine x plus sine squared x. I just did it on the previous page. I just did that FOIL. So that, now my right-hand side looks like my left-hand side. Check. So these are tricky. Like I said, on the quiz, I will put one that you have seen before. Assuming you watched the videos and did your homework, you won't have to do a brand new identity. You'll have seen it before.